This is Lab 1, constant velocity. The purpose of this lab is to examine position against time for an object with constant velocity using both experimental data and a computer model. In particular, we focus on Newton's first and second laws, as well as the kinematic equations for constant force. Overall, it was found that position is a linear function of time for motion with constant velocity, and that the experimental data very closely match the computer prediction to some minor error. In particular, the most important equation to focus on is the position update formula, which is derived from the definition of velocity. It states that final position is equal to the initial position plus the average velocity times the change in time. Also, because there's net force is zero, it's worth looking at Newton's second and first laws. Essentially, since the net force is zero, the change in momentum has to be zero as well, which would mean that the change in velocity is also zero. Both of them are essentially saying the same thing. And the reason that we're doing this is because we're assuming that net force is zero. That is, all the forces in the system cancel each other out. However, we're making the assumption that friction is negligible in the process, which isn't the case in reality because there is friction from the table on the object rolling as well as air resistance. So for the experiment, we'll essentially slightly push a roll of string across the table and record its motion after the push. So only the section with constant motion. And the tracker will be used to map position versus time. And so what this means is that the system is the roll of string and that the surroundings is the table and the air. It will be assumed that the initial position is 0, 0, 0, so the origin. The velocity is only the x direction and that the net force is 0 newtons. And so this is just showing the experimental procedure and the tracker system that was used. The meter stick is there for reference and scaling the data. Overall, it was found that there's a positive linear trend line between the position and time. In particular, this was the equation shown. And what this means is that the average velocity was the slope of the line. Otherwise, it's 0.2097 meters per second. You can kind of see if you match these up, that's where I'm getting this number. It's also worth noting the r squared value, which is very close to 1, which suggests essentially perfect correlation between the two. For the code, two major sections were edited to mimic the situation in the experiment. The first is setting the initial position to 0, 0, 0, the initial velocity to the value obtained from the graph, so 0.2097 meters per second to the negative 1, setting the net force to 0, the change in time to 1 over 30 seconds. And the other major section that was edited was inside the while loop to update the ball position. In particular, just the kinematic equation was plugged into the while loop. These are the results from the code, which also show the same linear trend line from the experimental data. In particular, this is just a trend line of the equation of final position is 0.2097 meters per second times the change in time. Overall, what this shows is that the experimental data and the code were very similar. The code is here in orange, which is a perfect straight line. You know, the experimental data is nearly a straight line with some slight error due to the following reasons. The first was likely just human error when using tracker. It can be very difficult to perfectly line up the center of the object at every time interval. Additionally, the other main source of error is friction from the table and air resistance, which would slightly slow the ball down. As a result, the net force would no longer be zero and the velocity would not be constant. However, this is likely not very significant due to the small scale and low speeds. Another thing worth noting is that if the x-axis were flipped, you would essentially just see a reflection of the trend line about the x-axis. That is, as time goes on, the ball is moving more and more negative x direction. Additionally, it's also worth looking at the forces in the system. Assuming that there's no frictional forces, the net force is just the force of gravity plus the normal force, which would cancel out because the force of gravity is perpendicular to the table. However, in reality, frictional forces, and that is the friction of the table on the roll, as well as air resistance oppose the motion, and the roll will slow down. As a result, there would not be constant velocity. So in conclusion, it shows that Newton's first law stands, and that for motion with constant velocity, position is proportional to time. This is supported by both the experimental data and the code. Additionally, it was also shown that the experimental data mostly matched the computer prediction and that the small margin of error was likely due to human accuracy using Tracker. Thank you.